On July 1st, 2025, a telescope in the Atacama Desert in Chile photographed something moving across the sky that did not belong here. Not belong here in the way that a stray dog doesn't belong in a library. Not belong here in the way that a tourist looks slightly out of place in a foreign city. Not belong here in the deepest, most fundamental sense of those words, because this object did not come from our solar system. It did not form around our sun. It was not born from the same ancient disk of gas and dust that built every planet, every moon, every asteroid, every comet we have ever cataloged. It came from somewhere else entirely. Another star system, another corner of the galaxy, a place so far away that the light from it takes thousands of years just to reach the lens of the best telescope we have ever built. And it was heading directly toward the inner solar system, toward Mars, toward the sun, toward us. Scientists gave it the designation 3IATLAS. The I stands for Interstellar. The 3 means it is only the third object of its kind ever confirmed in recorded human history. 3. In all of the centuries we have been watching the sky, in all the millions of comets and asteroids and bits of debris we have cataloged orbiting our own sun, only 3 times have we ever caught an object that originated somewhere else entirely and was just passing through. And this one, the third one, turned out to be unlike anything we were prepared for. Not because it was dangerous. It was not. I want to be completely clear about that from the start, because this story is strange enough without adding things that are not true. 3IATLAS never threatened Earth. It never threatened Mars. It passed through our solar system the way a traveler passes through a city they have never visited and will never return to, briefly, silently, without stopping. The closest it ever came to Earth was 270 million kilometers, nearly twice the distance between Earth and the Sun. It was never going to hit anything. But what James Webb found inside it, what the most powerful telescope humanity has ever placed in space detected when it analyzed the chemistry of this ancient visitor, is the kind of discovery that makes the most experienced astronomers stop mid-sentence and reach for their notebooks. Because what was inside 3IATLAS should not have been possible by any chemistry we have ever measured in any comet anywhere at any time. And what that tells us about where this object came from, how old it is, and what it was doing before our sun even existed, is more extraordinary than anything the people who invented it could have imagined. Stay with me because this is the real story, and the real story is better than anything anyone made up about it. To understand why 3IATLAS matters as much as it does, you first need to understand what it actually is and what the discovery of interstellar objects means for astronomy. Our solar system formed approximately 4.6 billion years ago from a rotating cloud of gas and dust surrounding a young star, our sun. As that cloud collapsed under gravity and began spinning, material in the disk gradually clumped together into planetesimals, then protoplanets, then the 8 planets we have today. Comets formed in the cold outer regions of this disk where temperatures were low enough for ices of water, carbon dioxide, methane, and other volatile compounds to solidify alongside rocky and dusty material. These frozen bodies carried the chemical record of our solar system's formation, a fingerprint of the specific conditions, temperatures, and chemical abundances present around our particular star at the moment our solar neighborhood was born. Every comet we had ever studied before July 2025 was a product of the same process. Every nucleus, every tail, every coma was made of material that formed here in our system from the same building blocks as Earth itself. We knew their chemistry because we knew their origin. 3IATLAS broke that entirely. Was briefly captured in the sun's gravitational influence, swung around the inner solar system, and will now depart, never to return. The sun's gravity is not strong enough to hold it. 3IATLAS came. It visited, and it left permanently. It will never come back. Within days of discovery, observations by David Jewett and Jane Liu using the Nordic Optical Telescope confirmed that 3IATLAS was, quote, clearly active, meaning it had an icy nucleus releasing gas and dust as the sun's heat reached it, producing a visible coma. That made it a comet, not an asteroid. And as more telescopes around the world turned their eyes toward it, the picture of what was coming began to take shape. It was big. Hubble Space Telescope observations as of August 20th, 2025, suggested the nucleus diameter was somewhere between 440 meters and 5.6 kilometers. That is a wide range. The uncertainty reflects how difficult it is to resolve a small, distant object moving at extraordinary speed. But even the lower end of that estimate made it a significant body. And it was moving at entry speeds approaching 250,000 kilometers per hour relative to the sun, fast enough, when you do the math, to cross the distance between Earth and the Moon in under 80 minutes. The trajectory of 3IATLAS brought it close to several of our solar system's inner planets, though safely distant from all of them. It passed closest to Mars on October 3, 2025, at a distance of 29 million km, close enough that spacecraft already orbiting Mars could observe it directly. It reached perihelion, its closest point to the Sun, on October 29th and 30th, 2025, passing just inside Mars's orbital distance. After that, it began the outward journey that would take it past Venus in November, past Earth's orbital zone in December, past Jupiter in March 2026, and eventually out of the solar system entirely, accelerating back to the same speed it arrived at, free of the Sun's gravity, heading into a galaxy it has been traveling through for longer than our planet has existed. And while it was here, every major telescope and spacecraft humanity has ever built pointed at it. Hubble watched it, James Webb watched it, TESS watched it, Sphere-X watched it. The Parker Solar Probe caught a glimpse as it rounded the Sun. Mars Reconnaissance Orbiter photographed it from Martian orbit. Perseverance stopped its surface exploration, tilted its cameras skyward, and took a picture of an interstellar comet, the first time a rover on the surface of another planet has ever photographed an object from another star system. ExoMars Trace Gas Orbiter imaged it. Mars Express imaged it. The Jupiter Icy Moons Explorer, the ESA spacecraft called JUICE, was close enough to observe it with multiple instruments as it rounded the Sunday. NASA's MAVEN spacecraft at Mars measured the gas production from its coma with direct spectral observation. This was, by any measure, the most comprehensively observed astronomical event since the last time a comet of this significance appeared. Every instrument, every spacecraft, every ground-based observatory that could possibly be pointed at this object was pointed at it. And the data that came back from all of those different instruments, from all of those different angles, using all of those different detection methods, began to build a picture of 3IATLAS that was genuinely unprecedented. Let me take you through what they found because each piece of it is more remarkable than the last. The first thing that stood out was the color. The coma of 3IATLAS, the cloud of gas and dust surrounding its nucleus, had a reddish hue. This same reddish color is found in what astronomers call D-type asteroids, in standard solar system comets, and notably in 2I, Borisov, the second interstellar object ever confirmed, discovered in 2019. The reddish color is thought to be caused by irradiated organic compounds called tholins, complex molecules that form when simpler carbon-based chemicals are exposed to radiation over extremely long timescales. The presence of tholins in 3I-Atlas's coma was scientifically interesting, not just for what it revealed about the comet's surface, but for what it implied about the comet's age. To accumulate the degree of irradiation consistent with a tholins-rich surface, an object needs to have been in deep space, exposed to cosmic radiation for an extraordinarily long time. Not millions of years, billions of years. This was the first hint of something that later observations would confirm in stunning detail. The second major discovery came from water, or rather, from the strange absence of it, as 3I-Atlas approached the Sun and its ices began sublimating, converting directly from solid to gas under the heat of solar radiation. Astronomers expected to see the same production ratios they had measured in other comets. Water, carbon dioxide, and carbon monoxide in proportions consistent with what forms in the cold outer regions of the solar system. That is what they found in 2I Borisov. That is what every solar system comet produces. 3I-Atlas produced something completely different. The carbon dioxide and carbon monoxide production rates were anomalously high relative to water. Not slightly high, significantly, measurably, unmistakably high compared to the patterns seen in any other comet ever observed. Researchers combining spectral data from NASA's MAVEN spacecraft, James Webb, and Sphere-X found that the relative water, carbon dioxide, and carbon monoxide production rates of 3I-Atlas differed substantially from typical comets. This chemical profile, this specific ratio of volatile compounds, had never been seen before. NASA researchers led by Martin Cordner at NASA Goddard provided one of the clearest explanations. If 3I-Atlas had a nucleus rich in carbon dioxide rather than water ice, it could mean that the comet formed at a specific distance from its parent star, the distance where carbon dioxide could freeze rather than just water, a zone called the CO2 frost line. Alternatively, it could mean that the comet had been exposed to extremely high levels of radiation over an enormous period of time, altering the relative abundance of its volatile compounds through long-term photochemical processing. Either explanation pointed toward a comet that formed under conditions around a star at a distance and in an environment that was genuinely and measurably different from the conditions that produced every comet we had ever studied before. Different star, different chemistry, different history entirely, and then came the methane. On June 22nd, in nearly a year after 3IATLAS's discovery and months after it had already begun its journey back out of the solar system, a groundbreaking study was published in the journal Nature. The lead author was Martin Cordner at NASA Goddard. The instrument was James Webb's NIRSPEC, the Near-Infrared Spectrograph, the most sensitive chemical detection system ever placed in space. What Cordner's team found in the data from that James Webb observation rewrote the record books for cometary chemistry. The methane-to-water ratio in 3I-ATLAS was roughly 11 times higher than any previously measured solar system object. 11 times, not 10% higher, not double. 11 times the methane-to-water ratio of anything we have ever measured in any comet, any asteroid, any object from our own solar system. A number so far outside the range of what our own solar system produces that scientists immediately understood it was not merely an outlier. It was a signal. A chemical fingerprint pointing unambiguously toward a place with different conditions, different temperatures, different chemistry, a protoplanetary disk around a different star far from here, long before our sun lit its first fires. Why does such a high methane abundance matter? Because methane is one of the most volatile compounds we know of. It freezes at extraordinarily cold temperatures, far colder than water ice, colder even than carbon dioxide ice. For a comet to contain methane in its nucleus in such extreme abundance, it would have had to form in an environment with temperatures far below anything in our own outer solar system. This points to a parent star system that was significantly different from our own, possibly colder, possibly a different type of star, possibly a formation zone at a far greater distance from its host star than any comet-forming region in our solar neighborhood. And then there was something else in the data, something that, when combined with the methane finding, turned a remarkable discovery into an extraordinary one, carbon-13. The isotopic signature of carbon in 3I-ATLAS was detectably different from what we measure in solar system objects. Trace amounts of carbon-13, a slightly heavier form of carbon, were present in ratios suggesting the comet formed in an extremely cold region where water ice frosted over at temperatures below 30 Kelvin. That is minus 243 degrees C. To put that in perspective, the average temperature of interstellar space far from any star is about 2.7 Kelvin. This comet formed somewhere almost as cold as the void between stars. When researchers combined all of this, the tholins suggesting extreme radiation exposure over enormous timescales, the unusual carbon dioxide to water ratios, the 11 times elevated methane, and the carbon-13 isotopic signature, they arrived at a conclusion that once stated is almost impossible to fully absorb. 3I-ATLAS is estimated to be between 10 and 12 billion years old. Our solar system is 4.6 billion years old. Our sun has not yet reached the midpoint of its expected lifespan. Earth, with all its billions of years of geological history, all of its vast evolutionary record stretching back to the first single-celled organisms, is a young thing by comparison to this comet. 3I-ATLAS formed approximately 7 to 8 billion years before Earth existed. When this object was young, the Milky Way galaxy was young, the universe was young, the generation of stars that had come before were only just beginning to die, seeding the galaxy with the heavier elements that would eventually form rocky planets, and billions of years later, everything alive on them. Martin Cordner, describing the finding, called it an ancient object, probably predating our sun and solar system. Those words, coming from the principal investigator of the study, carrying the weight of peer-reviewed analysis published in Nature, are not casual remarks. They are a statement that the oldest object ever directly observed by human instruments passed through our solar system last year, was photographed by a rover on Mars, had its chemistry analyzed by the most powerful telescope we have ever built, and is now on its way back out into a galaxy it has been crossing for longer than the Earth has been a solid rock. To understand why 3I-Const was here at all, and in fact why any interstellar object passes through our solar system, you need to understand something about the life cycle of star systems and the mechanics of how objects get ejected from them. When a solar system forms, not all the material that begins the process ends up in planets. A significant fraction of the comets, asteroids, and planetesimals that form in the outer disk are eventually scattered outward by gravitational interactions with the giant planets. Jupiter, in our case, does most of this work and flung into the far outer reaches of the solar system into a distant reservoir called the Oort cloud, or sometimes ejected from the system entirely. This ejection is not gentle. The objects that get thrown out are sent on hyperbolic trajectories that carry them free of the star's gravity forever into interstellar space, where they drift for billions of years without any star to warm them, without any light to illuminate them, without anything except the slow creep of cosmic radiation gradually altering their surfaces. The galaxy is full of these objects. Scientists believe that the number of interstellar comets, bodies ejected from their home star systems and drifting freely through the Milky Way, may be extraordinarily large. Some estimates suggest trillions upon trillions of them distributed across the galaxy's disk, invisible to any telescope because they are cold, dark, and moving between the stars where no light reaches them. We only detect them when one happens to pass close enough to another star, close enough to be warmed, to begin sublimating, to grow a coma and a tail, to become bright enough to be seen. 3IATLAS had been drifting through the galaxy for between 10 and 12 billion years before that moment on July 1st, 2025, when the Atlas telescope in Chile caught it moving across the sky. 10 to 12 billion years of silent travel through the void. No star to orbit, no system to call home, just the unimaginable scale of galactic space and the slow, steady march of time. And then, at some point in the last few tens of thousands of years, the trajectory of this ancient object curved toward our star. The sun's gravity began to pull it. It began to fall inward, accelerating as it descended toward the warmth it had not felt since the star system it formed in grew old and died. Its ices began to sublimate. Its coma began to grow. The dust grains that had been locked in its nucleus since before Earth existed began to pour outward at speeds of 22 meters per second, scattering into the solar wind. And a telescope in Chile photographed it moving against the background of the stars. The JWST data deserves its own moment of appreciation. ESA's Jupiter Icy Moons Explorer, a spacecraft designed to study the moons of Jupiter, found itself in an extraordinary position in November 2025, close enough to 31P, Atlas just after its perihelion passage, when the comet was at its most active, to observe it with multiple instruments including cameras, spectrometers, and a particle sensor. Because JWST was using its main high-gain antenna as a heat shield against the sun at the time, it had to transmit data back to Earth at a much lower rate through a smaller backup antenna. The team could only download a fraction of the observation data immediately. The rest of the JWST observations of 31P, Atlas only arrived on Earth in February 2026, months after the observations were made. This is the reality of doing science at interplanetary distances. You wait. You plan the observation months in advance. You configure the instruments for a target that is moving at 250,000 kilometers per hour and will never return. You wait for the data to make its slow journey across hundreds of millions of kilometers. And then, in the quiet of a February morning, the numbers start arriving and you find out what you saw. The image that emerged from the navigation camera aboard JWST, even just a quarter of the full image, downloaded first because of the data rate constraints, showed an active comet. The coma was clearly visible. The tail was developing. And the chemical instruments confirmed what the other telescopes had been beginning to suspect. This object was genuinely unlike any comet observed before. Meanwhile, the ExoMars Trace Gas Orbiter pulled off something that planetary scientists described as unprecedented in a different way. Using a camera designed to photograph the Martian surface just a few hundred kilometers below, the team pointed it at a target 30 million kilometers away and successfully imaged 3IATLAS's coma moving against the background of space. The image showed the slightly fuzzy white dot of the comet's coma, clearly distinguishable from background stars, moving through frames taken between October 1st and 7th, 2025. By triangulating these Mars-based observations with ground-based telescope data from Earth, ESA's planetary defense team was able to improve the predicted location of 3IATLAS by a factor of 10, a tenfold leap in positional accuracy, enabling every subsequent observation to be made with far greater confidence in exactly where the instruments needed to point. And Perseverance, the rover sitting on the floor of Jezero crater on Mars, tasked with searching for signs of ancient life in Martian rocks, paused its geological work, tilted its mastcam skyward on the cold Martian morning, and took a photograph of an ancient interstellar comet passing through the sky above Mars. An image taken on the surface of another planet of an object from another star system. Two extraordinary facts stacked on top of each other in a single photograph. Here is where the science stands as of June 2026. With the Nature paper now published and the broader astronomical community beginning to absorb what the 3IATLAS observations have revealed. The methane to water ratio of 11 times any known solar system object is the single most chemically anomalous measurement ever recorded for a comet. It is not a measurement that can be explained by unusual processing within our solar system, by the specific position of 3IATLAS's orbit relative to the Sun, or by any systematic error in James Webb's instruments. The near-spec spectrograph has been calibrated against known solar system objects and consistently produces accurate results. This measurement is real. What it means is that somewhere in the galaxy, around AA, that may itself no longer exist in a protoplanetary disk that formed 10 to 12 billion years ago under conditions our solar system never experienced. A comet formed with a chemical composition that is genuinely alien to everything we know. The conditions around that star were colder than the conditions in our outer solar system. The frost lines, the boundaries at which different compounds can freeze, were at different distances. The abundances of different molecules in the parent star's protoplanetary disk were different from the abundances in ours. And because we now have a direct chemical sample of that environment sitting in James Webb's spectral data, analyzed in a peer-reviewed paper published in Nature, we know something concrete about what conditions were like around a star we have never seen in a location we cannot identify at a time when Earth was not yet formed. This is what 3IATLAS actually is. Stripped of every invented detail, presented exactly as the science describes it. It is a chemical ambassador from another star system, a physical piece of evidence billions of years old that crossed the galaxy and passed through our solar system, carrying information about its origin, encoded in the ratios of its molecules. That information is now in our hands. ESA's planetary defense team described the tracking of 3IATLAS as a valuable test case for planetary defense, even though 3IATLAS does not pose any danger. Think about what that sentence actually means. The exercise of detecting, tracking, and characterizing an interstellar object on a hyperbolic trajectory through the inner solar system is exactly the same exercise that would be required if such an object ever did pose a danger. The coordination between ground-based telescopes, Earth-orbiting space telescopes like Hubble and Webb, and interplanetary spacecraft at Mars and Jupiter, all contributing data on an object moving faster than anything from our own solar system, has built an infrastructure of response that did not exist before July 2025. We are better prepared for the next interstellar visitor because of what we learned tracking this one, and the next one will come. Statistically, given the enormous number of interstellar objects believed to be drifting through the galaxy, it is not a question of if, but of when. The Vera Rubin Observatory, which has now entered its full survey operations, scans the entire southern sky every few nights with a camera so sensitive that objects which would have been completely invisible to previous sky surveys are now being detected regularly. The same survey science that enabled the discovery of 3IATLAS, which was spotted in data from the Vera Rubin Observatory's science validation period, 10 days before its official discovery date of July 1st, will continue to improve as the Rubin survey accumulates more data and more comparisons between images taken on different nights. Objects that cross the field between two observations leave a trail. Objects moving on hyperbolic trajectories stand out. The pipeline for detecting the next 4I, 5I, or 6I is already running. When the next interstellar object arrives, we will see it sooner. We will have more time to observe it. We will have instruments better calibrated for exactly this kind of observation because of everything the 3IATLAS campaign taught us. And we will have James Webb still operational, waiting to analyze whatever chemistry it carries from wherever it came from. I want to end with something that I think captures the real significance of a 3IATLAS better than any individual data point. For all of human history, for every century of every civilization that has ever looked up at the night sky, the stars have been lights, points of fire at incomprehensible distances, things to navigate by, to worship, to wonder at, to name. We have known for a long time that other stars have planets. We have suspected for decades that those planets have their own comets, their own chemical histories, their own records of formation in time. But knowing is different from touching. Suspecting is different from measuring. 3IATLAS gave us for the first time something to measure, a physical object, something with mass and chemistry and history that formed around a different star and traveled for 12 billion years and passed close enough to our instruments for James Webb to read its molecular fingerprint. The methane to water ratio of 11 is not just a number in a database. It is a data point from another star system. The carbon-13 isotopic signature is not just a spectral line. It is a record of temperatures that existed in a place we've never been, at a time that precedes everything we call home by billions of years. 12 billion years ago, something froze around a star we cannot see in a galaxy that was young and violent and still assembling itself from the aftermath of the Big Bang. That frozen thing drifted through the dying and rebirth of stars, through the flattening of the Milky Way's disk, through the formation of our own solar system, through the evolution of life on Earth, through the rise of human civilization, through every century of every generation of every astronomer who ever pointed a telescope at the sky and saw only points of light. And then, on July 1st, 2025, a telescope in Chile caught it moving across the background of those lights. We looked at it with every instrument we had.